I hope I'm audible. And first of all, sorry for the change in the dates of the class. I had some urgent uh, call because of which I had to change the class duration, class timing. So I apologize for that to all the students. And but let's hope I'm able to cover up the portions properly today. Once again, welcome back to week 7 of the problem solving session for the Introduction to Fluid Mechanics course by Professor Suman Chakraborty, uh, and I am the TA of this course. In this week we'll be discussing about, uh, or I must say, I should say we will start with the fluid dynamics part. Up till week 6, we have discussed about fluid statics and fluid kinematics, and I think by now all of the students are well versed with the fundamental concepts of fluid mechanics as well as the approaches used to solve fluid mechanics problems. But till now you would have observed that for the fluid statics part, our fluid motion was more or less stationary, and even if it was in motion, the fluid layers did not have relative motion, which allowed us to disregard the shear deformation of the fluid elements and thus treat this kind of fluid motion as are under the paradigm of fluid statics as well. Then we looked upon the concepts of fluid kinematics, which primarily depended on visualizing the flow field. Like, we were more or less concerned about the motion of the fluid around certain bluff bodies, or even just the motion of fluid in general, and try to visualize the different structures of fluid motion and try to understand it using flow visualization techniques such as streamlines, streak lines, and path lines. We also discuss our timelines, but as I mentioned, the primary tools of flow visualization for this fundamental or basic fluid mechanics course primarily relies on streamlines, streak lines, and path lines. And now, after all that, we have finally reached to the point where we are starting the discussion of fluid dynamics, where we will start discussing about the fluid in motion along with the forces that cause this kind of motion. So before that, we already briefly introduced about the equation of motion for this kind of fluid flows. That is the Navier-Stokes, but I guess unfortunately we have to wait for some time to get fully introduced or start using Navier-Stokes equation to model the equation of to model the fluid motion. Rather than that, today we will start our discussion on dynamics of in-viscid flows. And again, time and time again, we have iterated the importance of the dynamics of the importance of the understanding in-viscid flows. So let me just get back to it again. That, for example, like, of course, all of you might say that fluid motion or fluids are in general, not in general, all the fluids are viscous in nature, no matter how small their viscosity be or how large the viscosity be. But in general, no fluid is in viscous or in viscid. Then why study the in viscid flows? Okay, so let me just let me draw a diagram to help you understand the importance of that. And let me just again reiterate, we will again just briefly go through the concepts that we discussed in the class by Professor Chakraborty, and I will briefly go through them, the derivations, and take some problems, and finally we will again solve some problems that are relevant to this week's discussion that will be helpful for solving the assignments. I don't know whether the last day of submission has passed or not because of the shift in the class, but still it will be helpful for you for your exams. Okay, with that, let us just start our discussion. So the question was, why study in viscid flows? To answer that, let me just draw a figure that will, I guess, help you understand its importance. Okay, so this is a flat plate. Okay, and consider the flow over a flat plate. Okay. So what usually happens is that the for when the flow occurs over a flat plate, what happens is that there is a formation of a boundary layer. Okay. And again, I think in this course we will not discuss thoroughly about boundary layers, unfortunately, but still, let me just let you know about it. There is a formation of boundary layer. Okay. What boundary layer is basically like, it's more or less a demarcation between the regions of viscosity and regions which can be modeled as inviscid in nature. Okay, let me tell you the difference now. So consider that all the viscous effects, what happens is that in this boundary layer, all the strong viscous effects that are being felt because of the presence of the plate is being confined within a very thin region. Okay, within a very thin region, where this thin region is known as the boundary layer. Okay, whose thickness is, consider that if the length of the plate is say 1 meter, then saying that let's the let there be a flow of water over this flat plate, then the thickness of plate will be around in the order of millimeters. Okay, sorry, the thickness of the boundary layer will be of the order of millimeters. What it means is that all the viscous effects, for example, let me zoom in, let me like all the viscous effects such as the vertical structures that carry the information of the plate, of the presence of plate, from the plate to the outer flow is confined within this small region. Okay, so this region will be highly rotational and have highly viscous effects. Okay, and now you may say, what happens beyond this region? Okay, and this boundary is not a visible boundary, rather it's an imaginary boundary, but imaginary in the sense that it's not that it's not existent, but the fact is that it exists, but its demarcation is made in a way that the fluid mechanics or researchers have defined it in a way that it exists at a region where the flow velocity, let me consider again the incoming flow velocity to be say u infinity. Okay. Because of the presence of the boundary layer, what would happen is that because of the presence of the plate, the velocity at the surface of the plate would be equal to 0, right? Because of no-see boundary condition, the tangential velocity would be 0, and as we move along the surface of the plate in the vertical direction, say in this direction, the velocity will increase because of the fact that the upper sorry, just give me 1 minute. The upper layers of the fluid will try to drag the lower layers of the fluid in a way that it tries to accelerate the lower layers of the fluid, which will in general create the well-known velocity profile that we know, which is parabolic in nature. But that's the case. So the effect of plate is being propagated to the effect of this plate is propagated to the higher layers of fluid, which feels the presence of the plate by the virtue of its viscosity and the velocity gradients, of course. Or you can simply say by because of the shear stress. Now, what this boundary layer does is that it creates a demarcation by defining it in a way that we will say that the boundary layer extends up to a region where the flow velocity here is at 99% of your free stream velocity, that is u infinity. Okay, why 99%? I think it will be much more clearer when we go further into the topic of boundary layer in the last portions of this course, primarily because it's very difficult to find a region even in the vicinity of the plate which will tell us that the effect of boundary layer is almost absent. In that case only, the flow velocity will be equal to the free stream velocity, which will mean that the flow is not feeling the effect of the plate, which would in general be very very far away from the plate. But in order to make the analysis more simpler and logical, that's why, and we see that up to 99% of the free stream velocity, we can consider that up to that thickness we will consider our boundary layer to exist, which makes all the mathematical analysis much more simpler and makes the foundational study of boundary layer and fluid mechanics courses much more easier. That's why we are considering it. So now you may ask, what happens beyond the boundary layer? So the thing is that now beyond the boundary layer, viscosity is not zero. Of course, viscosity cannot be zero. It cannot happen that in the region below, like in the region within the boundary layer, viscosity is non-zero, and just beyond the boundary layer, viscosity suddenly becomes zero. It's not possible. Considering the continuum hypothesis, a sudden abrupt change in the physical properties of the fluid flow is not acceptable. So viscosity will essentially remain the same. It's a fluid property. If temperature remains the same, viscosity will more or less remain the same. So the viscosity is never equal to zero. But what happens is that the shear stress is defined by the product of the viscosity as well as the velocity gradients. So if shear stress has to be zero in these regions, the velocity gradients actually has to be zero. So what happens is that beyond the boundary layer, the velocity gradients are so small that they are not able to manifest the presence of the plate to these regions. That's why the flow the region more or less behaves like an inviscid region. Okay, it's not that viscosity is zero, but the velocity gradients are so small that the effect of plate cannot be manifested in those regions. Okay, so what happens is that in these kind of regions, which you can see is, if I think better it would be if I move this diagram a bit below. Okay, now, yeah. So now the thing is that, like, so if you wanted to say instead of this plate it was a bluff body, say it was a car. Okay, it was a car, and you wanted to understand or visualize the motion of fluid across the over the surface of the car, just to say do some uh, efficiency analysis, right, or aerodynamic analysis. So because of the very fact that the boundary layer or the viscous regions are so limited to a very thin finite region, and most of the region away from the car or just a few millimeters above the car are essentially inviscid, then the understanding or analysis of these kind of regions becomes very very important, or finding a way to understand the flow in these kind of regions becomes very very important, where the effect of viscosity is negligible. That's why the study of inviscid flows turns out to be one of the fundamental portions of any basic fluid mechanics course. Okay, so I hope with this the necessity of understanding or studying inviscid flows becomes clear. Okay, and as you know, our main equation or the foundational rock upon which the fluid mechanics is based is indeed Navier-Stokes equation. But for the scenarios where the viscous effects can be neglected, not saying it is zero but can be neglected, in those kind of regions our governing equation becomes the Euler's equation of motion. Okay, so let us try to derive it. Consider a 2D fluid element as shown here. We have taken a similar case previously, so I don't think I would repeat it again, but let us just go through it briefly. So considering the force balance, say, along the x direction, just to simplify our analysis, the pressure force that acts along this surface, say, would be pressure times area. Say let P be the pressure at this point, then area, and let the width of this fluid element, say, be 1. Okay, then your pressure would be P times delta y, correct? Similarly, now if we try to find the pressure acting at this surface, which will always be in the inward direction, so the pressure would be P plus dou P plus delta x, sorry, P plus dou P dou x times delta x plus delta y. So using Taylor series expansion, if P is the pressure here, and so pressure at, say, a distance of delta x can be found out using the Taylor series expansion. I'm suffering from a little bit of sore throat, so please give me a minute. Okay. Meanwhile, you can look into the derivation. Maybe you will be able to understand better. So just give me a minute. Yeah. So so I won't again repeat because we already discussed about the Taylor series expansion and how this approximation of pressure distance of delta x from a certain point is already be derived. So I think I won't repeat it. But if there's any doubt, of course you might ask. But for now, let us proceed. If there's any doubt, you can stop and ask. Okay. So this is the pressure at a distance of delta x, say from this point. Then now, if we do the force balance, and of course considering the body force to be rho bx, to be bx, the body force per unit mass to be bx, then a net body force along this x direction will be rho bx delta x delta y times 1, which will be the volume, right? Density times volume will give you the mass. Mass times the body force per unit mass will give you the net force along the x direction. Now from Newton's second law of motion, we have Fx is equal to delta m times Ax. So Fx is all the forces that are acting on the body. So we have the surface forces, that is the pressure, and the body forces, that is given by Bx. So if you write out these terms here, then we have P delta y minus P plus dou P dou x times delta y plus rho Bx delta x delta y to be equal to mass, that is density times volume, rho delta x delta y and acceleration, that is given by this, the Eulerian acceleration. Okay. That is dou u dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Now if you just simplify this equation, you will see that these terms will get cancelled out. So what you will be left out, and if you cancel out delta x delta y from all the terms, what you will get is that minus dou p by dou x plus rho bx is equal to rho dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Okay. Now we can classify these terms as the first term signifying the pressure forces, the second term signifying the body forces, and the final term signifying the inertial forces because of the motion of the fluid. Okay. Now let us consider an example, again already taken in the class, but let us just look into it. So we have a flow given by or a flow field given by V is equal to Ax I cap minus Ay j cap. Okay. So what you need to do is, let me just reiterate, what you need to do is, and here gravity acts along the negative z direction. Gravity acts along the negative z direction. Okay. And you need to find out the expression for pressure. Okay, find the expression for pressure. Since it's a 2D flow, pressure will also be a 2D scalar field. So since now and consider the flow to be inviscid. Okay, let me just reiterate it again. Then our question becomes complete. Otherwise, again we have to find the equation of motion for viscous cases as well. Okay, the flow is inviscid. So now we can directly come back and say, okay, flow is inviscid, then our equation of motion will be the Euler's equation of motion. So now if you substitute the value of the velocity field in the Euler's equation of motion along the x and the x, y and z direction, what you will get is minus dou p by dou x plus 0, because there is no body force along the x direction. You will have rho axa plus 0 because of course dou u by dou y and dou u by dou z is equal to 0, so these two terms are 0. I'm just writing the final form. You can of course check and calculate it, there is no problem in that, but we will eventually end up with this case. So you will have dou p dou x is equal to rho a square x. Okay, similarly minus dou p by dou y plus 0, because there is no body force along the y direction, so we will have rho 0 plus ay dot a, because we will see that, just give me 1 second again. You will see that there is no dependence of the y velocity component to the x and z coordinates, so the derivatives dou v by dou x and dou v by dou z would be equal to 0. So we'll end up with this equation. Okay, now if you integrate this, you will get p as minus rho a square x square by 2. Of course, integrate respect to x, you will have p is equal to minus rho a square x square by 2 plus some function of y and z plus some integration constant, say c1. Similarly, if you integrate this equation with respect to y, you will get p is equal to minus rho a square y square by 2 plus some function of x and z and some say some integration constant c2. Okay, now along the z direction you have dou p by dou z is equal to rho g, that is equal to 0 because there is a body force along the z direction, and of course there is no velocity component in that perspective, so this is equal to 0. Okay, so now if you integrate this with respect to z, you will get p is equal to minus rho z plus some function of x and y plus some integration constant c3. Okay, now similar to what we have done in the case of stream functions and velocity potential, if you remember, for partial derivatives we try to compare the function that we get after the compare the values of the arbitrary function that we get after the integration and see which satisfies the case. So if you compare all these three cases, what you will end up is that p would be equal to minus rho a square x square by 2 minus rho a square x y square by 2, I'm sorry, so x square, it's y square, y square by 2 minus rho g z plus some constant c. Now you know that ax and ay, if I go back here, are indeed the, so ax and minus ay are indeed the velocity components along the x and y direction respectively. So if you sum the if you sum both of these terms, okay, if you sum both of these terms, you will get something like minus of rho ax square plus ay square, sorry, a square y square. Basically it will be u square and v square, correct? So so let me just simplify it. I think some of you might be confused uh, now, might be confused by now, so let me just clarify it. So if say you have the velocity vector, say capital V, as u I cap plus v j cap, then the magnitude of the velocity vector v would be square root of, oh yes, square root of u square plus v square, which would be the square root of, in this case, a square x square plus a square y square, correct? So now if you square it, what you will see is that the square of the magnitude of the velocity field is indeed same as writing as square of the velocity field, magnitude of velocity field, that is v square, that will be equal to a square x square plus a square y square. So now if you use this simplification back into this equation, you will get P is equal to half rho v square minus rho zz plus g plus c. Okay. Now if you take these expressions in the left hand side of the equation, you will end up with P plus half rho v square plus rho zz is equal to some constant c, which is the Bernoulli's equation. Now you might ask, why in a arbitrary velocity field, when applied, and when we applied the Euler's equation of motion on an arbitrary velocity field given in this question, why we are ending up with the Bernoulli's equation? Okay, and this is actually the Bernoulli's equation. I'm sorry I have not introduced it yet, but this is indeed the very very famous form of the Bernoulli's equation. The reason behind reaching this form of Bernoulli's equation for an arbitrary velocity field is because this velocity field is indeed not arbitrary at all. It is devised in a way that it is, as you can see, both the rate of deformation is 0, okay, more importantly it is incompressible as well as irrotational, okay. And we will eventually see that for the Bernoulli's equation to be valid, or to derive the Bernoulli's equation, we impose certain assumptions, among which incompressibility and irrotationality turns out to be one of the fundamental assumptions that we use, okay. So yeah, so just to proceed further, or to just analyze this flow even further, let us try to find the equation of streamline for this kind of flow, okay. So we will have dx, the equation of stream again found out by using this equation. Dx by u is equal to dy by v. U is ax, v is minus ay. If you simplify this equation, you will get y dx plus x dy, which is the derivative of xy, d of xy. And if you integrate it, you will get xy term is equal to some constant. And this equation is the equation of a rectangular hyperbola. Sorry, I have made so many mistakes. It's actually rectangular hyperbola. You can look about it in the internet. You will see some interesting facts. For example, in the case of isothermal flows, the pressure temperature plot also turns out to be a rectangular hyperbola. Just in case if you're interested, you can look into it because it gives the similar relation. For isothermal flows, we get something like pressure and volume, specific volume. So volume in general is also correct. And for isothermal flows, let me just write it. We get the pressure volume relation to be something like this. You can see these are exactly similar or exactly the same. Just replace the uh, variables of p and v with x and y. You will get the same equation. So basically, what I'm trying to say is that in the case of isothermal flows, the pressure volume relation also turns out to be rectangular hyperbola. So the more details on this, you can look into it and you will find quite interesting to see, like why it is called rectangular hyperbola. Okay, maybe you can leave it as a homework for all of you. Like, of course, which I will not evaluate. No one will evaluate, but you can do it for your own benefit. Okay. So here I will wait for 4 minutes. Sorry for that. I want to give a bit of 4 minutes. I will say 3 minutes to give a bit of rest to my throat. Meanwhile, if there is any doubt in up till now, you can ask, because from now we will just dive deep to our discussion on the detailed derivation of your Navier the Bernoulli's equation. So yeah, so if there is any doubt till now, you can ask. But for now, I'll try to just wait for a few minutes to give my sore throat a bit rest. Okay. Sorry for today. Like there are so many problems. For example, you might be experiencing like because of the rain, the sound might be quite muffled even in the recorded video. So I'm sorry for that. Some things that we cannot control really. Moreover, I'm not able to speak loudly as the previous classes. Again, sorry for that. Like I'm still finding it difficult to speak because of the sore throat and the pain, but let us try to get over with it. Maybe we will be able to do it. Okay, so please don't mind for it, and I'm really sorry for the inconvenience. So what we can do is because of the present conditions, what I can do is let us try to go through these derivations a bit quickly than usual. Okay, primarily because my throat is not good. Like I'm really finding it difficult to talk, and it is like really uncomfortable for me. So I'm really sorry for that. And moreover, since there are very few students, so I think if there's any doubt you can ask, but since these derivations already there in the lectures, so I think like the detailed discussion can be found out there, but all the necessary steps I will discuss. Okay, so let us proceed. So we will try to derive the Bernoulli's equation starting from the Euler's equation of motion. Okay, now consider a streamline whose length is say dl. Okay, then the expression we can, in a vectorized manner, we can represent the streamline as dx I cap plus dy j cap plus dz k cap. Okay, now we know that if pressure P is a function of x, y and z, then the complete derivative or total derivative of pressure can be represented by this equation. It is dP is equal to dou P by dou x dx plus dou P by dou y dy plus dou P by dou z dz. Let us name this equation as star. Now from Euler's equation of motion along the x direction, we can write something like dP by dx is equal to minus of rho dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus rho bx. Okay, now you can easily do it. It is just a manipulation of the terms. We have just changed the very slightly manipulated the equation, so you can easily find it out how we did it. Okay, I don't think that should be any kind of challenging. Okay, there should be any kind of challenge in finding this form. So just give me 1 second. Okay, yeah. So what we will do is that we will try to in this equation we will try to replace the expression for dou P by dou x, dou P by dou y and dou P by dou z obtained from the Euler's equation of motion. Okay, so that is what we will do. Substitute the value of dou P by dou x, dou P by dou y and dou P by dou z in equation star. So once you do it, you will get a very lengthy equation given as this. Okay, so I will not read out each and every term. Maybe I will go through it. Like you can see, you will get something like dP is equal to this term 1 in this case plus this term. Okay, just to simplify that, this expression, that is u dou u by dou x plus v dou u by dou y plus w dou u by dou z can be written as v dot del times u. Okay, just to remove confusion. So dot del u would be something like u dou by dou x plus v dou by dou y plus w dou by dou z operating on u. So you will get u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Okay, so we have just simplified it, like represented this operation in a vectorial manner. Okay, we represented it as v dot del. Okay, okay. So yeah, if you just substitute the value of dou p by dou x, dou p by dou and dou p by dou z in equation star, you will end up with this long equation. Okay, you can do it like it's not that complex, it's very simple but just a bit lengthy, and just check the sign convention. Okay, just check the signs, don't misplace it, and you will easily get this form of equation. Okay, so just write it as term 1, term 2 and term 3. We will deal with all these terms separately. Now for term 1 we have simply, as you cannot simplify it even further, you can simplify it further, but maybe represent this in a vector form. Okay, so in a vector form you can represent term 1 as minus rho dou v by dou t, where v is the vector, velocity vector, times dl, where dl is dx I cap plus dy j k plus dz k cap. Okay, the second term, this one can again be simplified. It is in Cartesian coordinate system, so we can simplify it to the vector notation. So we will have this term will be there. Now we will have some product of velocity and streamline vector, right, or line vector in some sense. We will have this is say we will have v dot dl. Okay, so now we will see that you have a term something like v dot del operating on v. Okay, v dot del v. So using vector identity, you can easily find that v dot del v can be represented as half del operating on v dot v minus v cross del cross v. Okay, so it's I have just directly taken it from a vector identity. Okay, you can look back to your notes of vector calculus, you will get the similar relation. You can just find that out. Okay, and you can see that this del cross v is nothing but your vorticity. Correct? If you remember from the previous class, del cross v implies the vorticity. So I will represent it using the capital omega vector. Okay, which is this one. Now if you replace this in this equation, you will get minus rho times half of del operating upon v dot v minus v dot omega dot dl. Now term 3 is very simple. If we consider this body force components as the gravitational force, so bx and by 0 because the gravity x only along the z direction, so you will be left with minus rho g dz. Okay, g acting along the z direction. So now let us simplify the term to even further. Okay, so what you can do is, now v dot v will give you v square, or like in terms of its components, that is u square plus v square plus w square, is something that you already saw in the previous question. Correct? So the nebula operator operating upon v square can be represented as something like this, times this, because like we are just segregating, like it's operating on both the terms, so you'll have just like multiply dl with both the terms, so you'll have this term operate plus dot this minus v dot omega times dl. Okay, if you just take the multiplication, you will get minus rho half times dou by dou v square times dx plus dou by dou v square times dy plus dou by dou z v square times dz. Okay, or in simplified manner, it simply tells us this can be represented as half times d of v square. It is the complete derivative of v square. Considering that v is a we say v square is a function of x, y, and z, then this, from the understanding of, or from the expression of complete derivative in terms of its partial derivative, can be simplified as half times dv square. Okay, you can easily do it, so I'm not going to repeat it. Okay, so what you're left with, second term gives us the simplified form of the equation as minus half rho dv square plus rho times v dot omega dot dl. Okay, so if you combine term 1, term 2, and term 3, you will get something like dp is equal to minus rho dv dt dou v by dou t dot dl minus half rho dv square plus rho dl dot v cross omega minus rho g dz. Okay, now you can if you just shift these terms in the left hand side, you will end up with this equation. Okay, now you can see that there is some remnants of the much appreciated or much celebrated Bernoulli's equation that we eventually see. The pressure term is there, the velocity term is there, and the potential energy term is also there, plus some additional terms because of these two terms. So of these two terms, this term and the vorticity term. Okay, now what you will see is that this term this term will become zero under two conditions. Okay, first condition is that if, like, basically this term denotes a scalar triple product. Okay, again something to look upon. I am not going to do it, but it's a good practice if you look upon it. A simple brush up of your vector calculus knowledge. Okay, so now if dl and v are perpendicular to each other, then these two rows are collinear, like they are along the same direction. Then if these two rows are same in the same direction or along the same direction, this can be represented as a scalar product of, not, I'm sorry, as a scalar multiple of the other. Then in other words, the determinant of this would be equal to 0. Okay, so first is that if the flow is considered along a streamline, then this term is equal to 0. That's the first case. Second is that if, in fact there are three cases. If the flow is irrotational, then again this term is equal to 0. Then the streamline being, then the flow being along the streamline is not a necessary condition. And the final consideration is that the product of v cross omega has to be perpendicular to dl, okay, which is again a very specific case which usually doesn't occur in any kind of analysis. Like that I know of. Like maybe in some special research analysis they may do it, but for most of the cases, like, we do not really consider this third case. But if somewhere or another the flow is rotational and as well as is not along the streamline, and if this third condition is satisfied, then also, fortunately or unfortunately, this term becomes equal to 0. Okay, but usually it's the mix of the first two terms. Like, either we consider that the flow is along a streamline, so we consider the first term to be 0, or we'll say that the flow is irrotational itself. And you will see that if the flow becomes irrotational, then the equation becomes, or applicability of the Bernoulli's equation becomes much more universal, much more, like, useful. Okay, so let us move further. I hope it is clear till now, so I will wait for 1 minute. Funny enough, for two reasons, like just to give a bit of rest to my throat and for all of you to digest what we have discussed till now. Okay. give me 1 minute, one more minute. Okay, I'm just coming. Okay, just one more minute. Okay. Meanwhile, you can look into the derivation here. Try to make it try to understand it. I'll cover it eventually. Okay, just give me 1 minute. Okay. So once again, sorry for the delay. Okay. So yeah, what we see is that now, yeah. So if I move back, we are left with certain terms like if either of these three assumptions, primarily these two assumptions for most of the practical cases are considered, then this term is essentially equal to 0. So we are left with these four terms. Okay. So now, if we consider the flow to be steady, let us consider one simplification case. Consider that the flow is steady. If the flow is steady, then this term like automatically becomes 0. Okay. So if this term becomes 0, then the equation that we have in our hand is something like, if the flow is along a streamline and the flow is steady, the equation that we have is dp plus half rho dv square plus rho g dz, which is the Euler's equation of motion along a streamline for a steady case. Okay. Now what we'll do is, we'll integrate this equation from say point 1 to point 2. Okay, considering that we are doing Eulerian approach and just looking at 2 points in the control volume, trying to analyze the flow conditions across 2 points in the control volume, say at the inlet and exit, or say anywhere in the point of our interest, considering an appropriate control volume, what we will get is this equation. Okay. Now if we consider a further simplification case where say density is itself constant. Okay, because till now we have not said anywhere the density is constant, like it's the consequence of our derivations that kept this density out of any kind of derivatives or any kind of calculations. Okay, but still we will see eventually, like if we consider that now the let density be also be constant, now in from this integration density can be taken out. So what we will left out will be p2 minus p1 by rho plus half v2 minus v2 square minus v1 square plus g times z2 minus z1 equal to 0. Again, if we just simplify it, take the terms with the subscript of 1 in the right hand side, you will end up with the much celebrated Bernoulli's equation, okay, which is usually the Bernoulli equation that is being discussed in most of the textbooks. Okay, introduced as the equation of fluid motion into textbooks. I still remember, like, this was the first equation of fluid motion that we were discussing about when I was in class 11. Okay, or, still in, at least in our India, this is class in class 11. This is the equation that they basically start with as an equation of motion of fluid. Okay, but now you know that it's not the case. It's actually a very very specific case of fluid motion where we can apply Bernoulli's equation, not questioning its applicability. Like, more or less, Bernoulli's equation gives us an idea of the variation or trend of variation of pressure and velocity even in very complex cases. For example, for flow and airfoil, it's through the principle of Bernoulli's equation we can say that, we can vaguely say that the pressure in the under the airfoil would be higher than the pressure above the airfoil. primarily because we are saying that the velocity on the upper surface of the airfoil is higher because of the curvature than the velocity at the lower surface, and because of this Bernoulli's principle, we can say the pressure at below the surface airfoil surface will be higher than the pressure on the upper surface of the airfoil, which will give us the required lift. But now we know that for at least from interpretation purpose, it's good, or it can be it can be applicable in most, in like in generally in most of the cases, and I would say many cases. But for proper analysis, proper accurate analysis, you now know that this is not the case. It's a very specific scenario where we can apply Bernoulli's equation, and this specificity can be boiled down using this four approximation. This very important four approximation, and I am sure that you will end up with questions in your this NPTEL exam, your assignments, as well as in your university exams, or even your GATE and ESC exams, or any state engineering examination. You will end up with questions related to assumptions used for deriving Bernoulli's equation. So let us just briefly go through them, and then we will proceed further. Okay. So these very four important assumptions are: first, the flow has to be inviscid. We started our derivation of Bernoulli's equation from Euler's equation of motion, which itself is based upon the assumption that the flow is inviscid, so it has to be there. Secondly, this form of the Bernoulli's equation, this very form, like unless and until specified, Bernoulli's equation is this equation. Okay, as I wrote it here, like there are unsteady form of Bernoulli's equation as well, which can be used, which we'll eventually see today. But unless and until mentioned, the Bernoulli's equation means this equation without the unsteady term. So the flow has to be steady. Third is density is constant. Okay, which is the special case of incompressible flow. Okay, but density is equal to constant was not needed for Euler's equation, if you remember. Okay, we never stated that density is constant in Euler's equation of motion. Okay, and finally, the final assumption is that the flow has to be, and this equation is valid along a streamline. That is, these points 1 and 2 are along the same streamline. Okay, and this is the assumption that people usually miss out or mistake, or do the most of the mistakes in this assumption, that in arbitrary case this equation is only valid if the 2 points are along the same streamline. Okay, but as it is written here in red, that this approximation can be relaxed if the flow is irrotational. So if the flow is irrotational, then this Bernoulli's equation can be applied at any 2 points in the flow field, of course given that the previous 3 assumptions are valid. Okay, so I will just give you some moment or some time to digest or take in this blue and red paragraph, or this blue or red. These are very important. Like I sometimes find it very depressing that students don't appreciate the importance of the assumptions that we make while deriving these equations. Okay, so I don't want the participants of this session to be something like that, so I will maybe forcefully tell you to take time and get these assumptions clear in your head before applying Bernoulli's equation in any kind of problem. Okay, okay, so let us proceed further. I hope you looked into or read into all these assumptions carefully. So with that, let us try to proceed further. Okay, these are the same discussion that we had, so I will proceed further. Maybe we will skip it. So now the question is, what does this Bernoulli equation actually represent? Is it the equation of motion for fluid, or is it not? So we know the answer, basically it's not. course it's the equation of motion, given that we apply the very strict assumption that we already showed in the previous uh, just before, like just we just now saw what are the crucial assumptions that has to be made. But even after that, what it basically represents, okay, so what it basically represents is energy balance, okay. So in the previous equation, we discussed in the previous classes, we discussed briefly about the continuity equation, which is the fundamental equation for mass conservation, correct. Then Euler's equation of motion, which is more or less the equation of momentum conservation for, or I'm sorry, which is the equation of momentum conservation for inviscid flows, okay. And Bernoulli's equation, in fact, is in a way the equation of energy conservation for flows which satisfies the given four assumptions, that is, flow has to be inviscid, density, the flow has to be steady, the density has to be constant, and has to be along a streamline, okay. And these three terms, as you can see here, represent the respective energy contributions, okay. The simplest one is the Z1 term, which basically represents the potential energy head, okay. Usually, like if we present it in the head form, we will tell that these terms represent, say, the potential energy head, the kinetic energy head, and the flow energy head, okay. Our beloved Professor Chakraborty, like, he took a lot of time to let us know that this is not the pressure energy, but indeed this is the flow energy, okay. The discussion of which is shown here. I think I may skip it for maybe because it's already discussed very thoroughly and very beautifully in the lecture. Like, I encourage all of you maybe to go back to the lecture and just look into it, like how beautifully our Professor Chakraborty takes time to make us understand why we tell it as the flow energy, okay, because it's basically the energy required to maintain the flow across a particular cross sectional area. That's why we tell it as the flow energy, okay. So maybe maybe you can just go back and look into it. Sorry for like taking much time, but this is important, okay. So the term Z1 represents the potential energy head, or in this particular form of equation, the potential energy per unit mass, sorry, per unit weight, because we are dividing it by mg. So potential energy is basically mgz1. So mgz1 divided by mg would be just leave you the head or the height. It is the potential head. The second term is v square by 2g, which is the kinetic energy head, okay. Half mv square divided by mg will give you the same term. We'll have v square by 2g. And the third is flow energy per unit weight. That is the work done per unit weight to maintain the flow in the presence of pressure, okay. Like certain amount of work has to be done to maintain the flow against the pressure that exists. So that's why it is known as the flow energy, okay. So the details or the thorough discussion on how this is obtained, maybe you can go back to the lecture. I think I will only do injustice to what he did in the class if I try to go and explain it. So maybe you can go to the lecture and try to understand it. It's very beautifully explained, and I do not think any other textbooks usually do so much emphasis on trying to make us understand what does this term usually signify, okay. So as a formal definition, Bernoulli's equation states that the flow energy, the kinetic energy, and the potential energy per unit weight remains conserved as it is transmitted from one point to another in the flow field. In this particular case, along a streamline, okay. Now let us discuss the unsteady part, okay. In the previous case, the Bernoulli's equation, as I mentioned, unless and otherwise stated explicitly, represents the steady part, okay. where the unsteady term is absent, only the flow energy term, that is the pressure term, the kinetic energy term, and the potential energy term are there. But there are some instances or cases or problems where the unsteady form of the Bernoulli equation also becomes important, which we will discuss now. Okay, so we have, for an inviscid flow along a streamline, the Euler's equation of motion can be represented as this equation. Like, it is simply the same one that we have discussed already. We have just brought back the unsteady term. Okay. Now we can just, what we can do is say, if this represents, ds represents the length along a streamline or along the streamline coordinate, then we can write ds as epsilon s cap, which is the, say, if we just do a simple change of coordinates from Cartesian to streamline coordinates, which we'll again discuss briefly, and maybe we'll take some examples in the next week's class about the streamline coordinate system. But if you do that, you can represent ds as epsilon s cap ds, that is a magnitude, times the unit vector along the streamline coordinate direction, and the velocity vector, that is, say, along the streamline direction, would be es cap v. Okay, es cap times v, where v is the magnitude. So if you simplify this dot product, you will get something like minus rho dou v by dou t ds. Okay, now for rho equal to constant, you will have equation as, you will end up with this equation. Okay, half 1 by rho dp integrated from 1 to 2 plus half of dv square integrated from 1 to 2, and g dz integrated from 1 to 2 is equal to minus of dou v dt ds integrated from 1 to 2. Now if you carry forward the integration, you will end up with the same Bernoulli's equation that we already discussed, but along with an additional unsteady term. Okay, if you just, as I mentioned, segregate the terms with the subscript of 1 and 2, the final form of the equation that you have in hand is given by this. Okay, which is the unsteady Bernoulli's equation. Okay, now we consider a case where the flow is irrotational. Okay, now if the flow is irrotational, as I mentioned, this equation becomes valid for any two points along a streamline, but not this. Bernoulli's equation becomes valid across any 2 points along a streamline. Let us see what happens if we consider, for this case, if the flow is irrotational. Okay, so if the flow is irrotational, you can represent the velocity vector as the gradient of a scalar field, which is the velocity potential. By now you know already. So we'll have del cross v is 0, so v is nebula times phi, or which in Cartesian coordinate can be represented as this one. Okay, now dl is I dx, dl would be I cap dx, dx I cap plus dy j cap plus dz k cap. Now if you just simplify this expression, substitute the value of v in this expression, you will get dou by dou t of dou phi dx, dou phi dou x dx plus dou phi dou y dy plus dou phi dou z dz. That would be equal to the complete derivative of dou phi by dou t. Considering that phi to be a smooth function, you can just interchange the order of derivatives, so you will end up with this expression. Okay, it's very simple. You can just take the derivative inside. Instead of it being phi, just take it as dou phi by dou t. Now consider dou phi by dou t is a function of x, y, and z, so you will end up with this equation. Okay, it's very simple. So if you just substitute this equation, if this expression in back to the inviscid Euler's equation, then the Euler's equation of motion for inviscid irrotational flow turns out to be this equation. Okay, now there are some, let us just discuss some of the theoretical aspects that was discussed in the class. There is factors that can make an originally irrotational flow rotational, that can convert an irrotational flow to a rotational flow. Okay, first is the presence of a solid boundary, that is, plus viscous effects. So if, say, the flow is initially irrotational, okay, then to make that flow irrotational, you have to have some external factors. So solid boundary acts as a generator of vorticities because of the no slip boundary conditions. So that can make the initially irrotational flow to be rotational. Okay. Then there are some other things that we will not discuss in this course. That is presence of shock waves. Like this term, you might encounter if you take some uh, fluid mechanics 2 course, where essentially they discuss say incompressible flows. So there they may briefly discuss about shock waves. Okay. Then there's thermal certification. Like if there's density variations, then that can generate rotationality in the flow, and Coriolis forces. Okay. So the very famous statement that relates to this discussion is that if the flow is inviscid and irrotational, okay, then it will remain irrotational even if the boundary is solid, even if the solid boundary is present, or basically it will remain irrotational forever, even if it encounters any kind of solid boundary. Why? Because if the flow is inviscid, then it will not experience the effect of solid wall, because there is no viscous effects that can manifest the presence of the wall through the velocity gradients. That's why even if there is solid boundary, and if we have or able to generate a flow that is able to flow that fluid through that particular say duct or channel, which is initially inviscid and in rotation, it will forever remain inviscid and in rotation in that particular flow. Okay, of course it's a very hypothetical scenario, but this statement helps us to clarify our concepts, like what are the effects or sources that can generate rotationality in the flow. Okay. So now let us discuss the streamline coordinate system. So I will briefly discuss it, because and like the details of the derivation, like how the Euler's equation of motion along the streamline coordinate and the normal direction are derived, I won't do. It's a basic change of coordinates from a Lagrangian, I'm sorry, from a Cartesian to a streamline coordinate system. So maybe you can look into it in the lectures. I'm really sorry that I'm not covering up in this discussion. Okay. So I'll just quickly go through it. Maybe primarily because I think we do not have examples related to this topic for discussion today, but you can go to the equation. We can go to the equation today, and maybe we'll cover up some examples in the next week's discussion. Okay. So if this is say this blue line represents a streamline, then the streamline direction or streamwise direction can be represented to be in the direction along the tangent of the streamline. That's why this particular direction represents the streamwise direction or tangential direction, where the unit vector is represented as es cap, and the direction normal to it would be the normal direction represented as epsilon n cap. Okay. Then the respective form of the Euler's equation of motion along the streamwise direction and the normal direction can be represented as is in these two forms. Okay. So you can just look into it, and I think even if there are no questions, I will try to take one example that helps you to understand this to the applicability of understanding the Euler's equation of motion along the streamwise direction and the normal direction. Okay. So I will take one example in the next week for sure. Okay, just to cover up this portion. So for now I will just, it's already shown here, you can just look into it, but I will repeat it in the next week's discussion. Okay, please don't mind. Okay then, so if it's clear now, let us take some examples. Okay, so let us look into the first question. Okay, the Euler's equation of motion is a statement of mass conservation, mechanical energy balance, conservation of linear momentum for a real fluid, conservation of linear momentum for a flow of an inviscid fluid. Okay. So since there are very few students, so I think what I can do is, as I usually do if there are very few students in the class, I will discuss the solution right away, because that would be better practice since there are very few number of students. So I will discuss the solution. If anyone is watching the video, this video for the reference, what you can do is you can kindly pause the video right away, right now. Here you can pause it here and try to solve it out or sort it out, think it out what will be the solution, and then once you get the solution, maybe you can just play out the video again just to check whether the solution is same or not. Okay, so this this solution is again very simple, like we already just discussed now. Where we use the Euler's equation of motion is option number D, is basically the equation of motion for fluid for inviscid flows. Okay, so it's a equation of conservation of linear momentum for inviscid flows. Okay, so option D is the correct answer. Question number 2 is the Euler's equation can be represented as, here rho is density and P is the thermodynamic pressure, V is the velocity vector, and B is the body force per unit mass. So they're basically asking us what would be the vector form of the Euler's equation of motion. Okay, again it's very simple actually if you already know, but these options are made in a way to confuse you. Okay, so you can pause the video now. So let me tell you the answer now. So the correct answer would be option number B. It's very simple actually. I don't think I need to repeat it why. It's basically Navier-Stokes, just the viscous terms are missing. So it's viscous, when viscous terms are there, this will be the final form of the Navier-Stokes equation. In fact, there are again certain assumptions that we have made here. Maybe we have considered Stokes hypothesis, which is valid for most of the cases, which is the final form. That's why the Navier-Stokes equation. Okay, but this is actually the most famous form of the Navier-Stokes equation. So this would be, and if you just disregard this term, like if you just disregard this term, like disregard the viscous effects, then this becomes the Euler's equation of motion. So option B is the correct one. Question number 3 is the Bernoulli's theorem deals with the law of conservation of which of the following cases? A is mass, momentum, mechanical energy, and concentration. Okay, so first of all, let us just do some process elimination. It cannot be about concentration because we are not discussing about mass transfer. Okay, so mass is conserved in our case, so that's in our discussions, so we are not discussing about the mass transfer, so it cannot be about concentration. Sorry. Second is mass. So we already saw the form of the continuity equation and the mass conservation equation. It was different from Euler's equation, so it cannot be mass conservation. So the confusion relies in between momentum and mechanical energy. So we already saw that the much appreciated form of the momentum conservation for fluid motion is the Navier-Stokes and the Euler's equation of motion, and we saw that none of them resembles the Bernoulli's equation. And so from the process of elimination itself, we can say that the only term that makes sense is the mechanical energy term, which is indeed the correct answer. But once again, if you just even remember the form of the Bernoulli's equation, you will realize that it indeed deals with terms that has energy inherent to it. For example, it has the term of say mgz, which represents the potential energy. Similarly, we have half mv square, which is, I think, the expression of kinetic energy in any form, any kind of physical discussion. So if you have an expression that or equation that is dealing with summation of terms which are the most popular forms of energy, that is the kinetic and potential energy, you can know that from the principle of dimension homogeneity, this equation has to be something related to energy conservation. Okay, so in this case, this is the conservation of mechanical energy. Okay. Question number 4. What does the following form of the Bernoulli's equations theorem signify? Okay. P plus rho g plus v square by 2g plus z is equal to constant. So what does this signify? So again, if you remember, we already told that this term represents the potential energy head. So potential energy head, that is potential energy head. So we have potential energy something like mgz. You can just directly start with mgz. Now what we can divide it with to get z. So if you divide this with mg, you will get something like this one, z. You will end up with z. So since you have divided it with mg, which is weight, so the correct option will simply be energy per unit weight. Okay, similarly you can check for kinetic energy as well. This is the kinetic energy head. So we'll have half mv squared by mgz, sorry, mg. If you just cancel out m, we'll have v squared by 2g. Okay, so let us look in the next question. Question number 5. What are the assumptions for the Bernoulli's equation of this form? Okay. Maybe I think you can look into it for a while. We have given so much time in understanding the assumptions, so I think it's a good time for you to revise. Okay. Okay, so we saw that our popular assumptions or the important assumptions were steady flow, rho is equal to constant in viscid and along a streamline. Correct. So let us check what does the options say. So option A seems correct. A is correct. Steady constant density, yeah. Again, this form is again correct. For irrotational flow also is correct because yes, this correct, right? For steady incompressible flow in this case, correct, because you can apply then this equation to any 2 points along in the flow field. Option C is also correct. Maybe there can be some kind of ambiguity, like people may say like, sir, incompressible does not mean the density is constant. It might happen that the two terms in the mass conservation may cancel out each other effectively. Yes, correct. But density is equal to constant also implies incompressibility, right? So in that way, this term is options also correct in that way. So in this case, you will see that all of the options are essentially correct. Okay, so option D is the correct option. Okay. Let us look into the next question then. Okay. Bernoulli's equation is applicable between any 2 points in the stream in the flow if any rotational flow of an incompressible in any rotational flow for an incompressible flow, any type of rotational flow of the fluid in a steady in viscid rotational flow of an incompressible fluid, in a steady in-viscid irrotational flow of an incompressible fluid. Okay, now you can choose the correct answer. So you can see that, as we already discussed, Bernoulli's equation is applicable for any 2 points in the flow field if the flow is irrotational. But given that it has to be steady in viscid as well as incompressible or constant density, so this option D would be the correct answer. Okay, so question number 7 and 8, I think we have to do some discussions. So what I will do is, let us go through the question for anyone or for the viewers watching the video, the recording of the video. So what I will do is, I will let us go through the question once, then directly I will start discussing the answer. Okay, unfortunately we do not have many participants today, so I will directly go discuss the answer. Okay, then but again what you can do is, you can maybe stop the video and then try out your own solution, which I will very highly appreciate, and then again get back to the just play the video again to see whether the answer is correct or not. Okay, so the question is, a rectangular chip floats on the top of a thin layer of air above a bottom plate, and air is blown at a uniform velocity v0 through the holes in the bottom plate. Okay, so it's something similar to what we have discussed in the previous class. Like, there was a porous wall where velocity was injected through the pores, similar to that. The width of the chip perpendicular to the plane of the figure is L, and for steady in viscid constant density flow, oh, there are so many assumptions now. For a steady in viscid constant density flow, the weight of the chip that can be held in equilibrium by the air injected is, that's the question. Okay, so if you are the weight, then it seems that we need to do something with the, we need to find a pressure field, right? To find the pressure exerted by the plate on the, or by the pressure exerted by the flow of the fluid from the pores to the plate, because, right, basically there is a plate here and there is air being injected in this direction, so this motion of fluid will try to balance the weight of the plate. So we need to find the weight of the plate. So for that, I think we need to find the pressure now. Okay, so let us look into the solution. So now maybe you can pause the video. I hope the question is clear, and then try out your answer. Okay, so, or yeah, so this is the I think, yeah, this is a schematic representation of the problem in hand. Like, the air has been injected through the pores from the bottom wall. Okay, and there's a chip being balanced because of this flow of fluid, but since the outer periphery, the periphery of the region between the wall and the chip are, what to say, not covered, then the fluid will get ejected out of these regions. Okay, so that's why there is a flow in the outward direction as well, as shown by these arrows. Okay, so we'll have air be injected through the pores at a velocity of v0, say, and let the velocity coming out along this direction be some velocity u of x. Okay, now the thing is, we are considering this velocity to be of uniform profile primarily because we are not considering the viscous effects. If the viscous effects would have been there, it would have something of profile like this. Okay, where no C boundary condition would have resulted in the velocity profile to be distorted near the walls. Okay, so from mass conservation, we'll have, and let this be the control volume. Okay, let this be the instantaneous control volume in hand. Okay, and let this length be, say, x. So we have, from mass conservation, v naught times your area would be x times L. L is the perpendicular width of the plate, so area would be x times L. So v naught x times L would be equal to u of x times L times h. Okay, like we are initially considering it to be a function of x. It can be a function of y as well, but you will eventually see that it ends up to be a function of x only. That's why we consider this velocity along the x direction to be a function of x only. Okay, in this case, and you will see that from mass conservation we get u, the velocity along the x direction, that is coming out of the periphery of this, the region between the chip and the wall, to be v naught x by h. Since v naught and h are constant, so this is a function of x only. Okay, now what you need to do is you need to find the weight of this chip. Okay, so from all the students that I usually teach in these sessions, I usually say that for any kind of mechanics problem, when you start with and you are ambiguous of how to proceed, always start to, like, of course use your logic. Of course I won't say that just do whatever I say, but for example, in this question now we have to find a weight. Now, like, if I also, like, had practiced similar problems a lot of times, that's why I know that now I have to use the momentum conservation to find an expression of pressure. But say for example you are starting today, and like you do not know what to do, you will just, I guess from my own personal experience, I can say you might get stuck, like what to do next. So the general thumb rule that I usually suggest them is that for these kind of scenarios, start with the mass conservation. Okay, for any velocity kind of relations, like if you need to find velocity or any relation in terms of velocity, because in these kind of problems mostly they will either give you the velocity profile at a particular cross section, or they will give you the mass flow rate. Okay, so in this case, one way or another, you will be able to find a relation or a velocity expression of velocity at the other exit, considering the Eulerian approach. So from mass conservation, you can easily find out that you can find the expression of velocity. Now the next thing is force, right? That can be asked. What is the net force? So now, since they are asking the net weight, which is essentially one interpretation of force, because the unit of weight and force are same, that is Newton. So now the next step would be to let us try to discuss this problem in terms of, say, momentum conservation. Okay, let us now apply the momentum conservation equation. Let us see what we get, and more or less eventually you will end up with the same the correct answer. Or in other words, other than this, like if you're dealing with subjective type of questions in your university exams or even state engineering exams, if the examiner sees that you're approaching in a way, like started with mass conservation, obtain simulation, now you're approaching the problem from the perspective of momentum conservation, the examiner will know that you're going in the right direction. So that's the general thumb rule. So we apply that. We already found a velocity, so next thing is force. So let us start with the momentum conservation. Since the flow is inviscid, you just simply apply the Euler's equation of motion, which will exactly do. Okay, so we have dou p by minus dou p by dou x plus rho bx is equal to rho ax. Okay, now since the body force along the x direction is equal to 0, so we'll have minus dou p by dou x is equal to rho ax. How to find ax? Ax is simply the Eulerian acceleration. Just substitute the value of u, v and w in this expression. Now since already know that it basically gives us a one-dimensional flow with and also, since u is a function of x only, you can see here, so all the other derivatives u and dou u by dou y and dou u by dou z are equal to 0, so and of course there is no unsteady term, so we'll have ax is equal to, you will only end up with this term, the convective acceleration part along the x direction. Okay, so we'll have ax is equal to v naught x by h times dou u by dou x is v naught by h, so we'll have ax is equal to v naught square x by h square. or dou p by dou x to be equal to rho v naught square x by h square. Now if you integrate this equation, you will get pressure P is equal to rho v naught square x square by 2h square plus some constant C1. Now to find this constant, you need to apply some appropriate boundary conditions. Okay, so one boundary condition would be that, let us go back to the diagram, that at x is equal to b by 2, like if the b is the width of the plate, then considering the symmetry, like at this point from here to here, the length will be b by 2. At x equal to b by 2, the pressure would be the atmospheric pressure, correct? So if you apply that boundary condition, you will get the value of the integration constant C1 as PATM plus rho v naught square b square by 8h square. Or if you substitute the value of C1 in this expression, you will get PS equal to PATM plus rho v naught square by 2h square times b square by 4 minus x square. Now the total force that acts on the plate would be 2 times integration of 0 to b by 2. Like if I go back again in the diagram, I'm sorry for scrolling back to and fro so many times. We have only considered this half part of the problem, like because of the symmetry. So we can also consider, like considering the problem to be symmetrical, so the integration would be basically integration of even problem or even function. So rather than integrating from say minus b by 2 to plus b by 2, let's integrate integration of 2 times 0 to b by 2. Okay, that's what we are doing. Integration of net force will be integration of 2 times integration of 0 to b by 2, and pressure times the area. Force would basically be pressure times the area, right? So basically, let me go back again. I'm sorry. The pressure exerted by the flow of fluid is balanced by the weight of the plate. So consider that the plate is in equilibrium right now. So the weight of the plate will basically be the pressure force exerted by the fluid on the plate. Okay. So the pressure here, since that the pressure on the upper surface of the plate is the atmospheric pressure, so pressure here has to be the excess of the atmospheric pressure. Okay, and the pressure that we got after the Euler's equation is indeed the absolute pressure, not the relative pressure. So pressure times area, so we take the relative pressure or the gauge pressure, in other words. We'll have integration of 2 times 0 to b by 2 times P minus P ATM, the gauge pressure, times area, that is L dx. Okay, so we have just now replace this expression here. What you will get, if you carry forward the integration, you can just check the calculations. I'm not going to read each and every term. So if you carry forward the integration, you will get F net as rho v naught square L b cube by 12h square. Now for equilibrium condition, F net would be equal to the net weight of the plate, that would be equal to rho v naught square L b cube by 12h square. Okay, so if you go back to the expression, so the final answer would be option A. Okay, so the final question is, again, it's a bit lengthy. It's again a numerical problem. So I'll read the question. You can pause the video. I'll discuss the answer, and maybe then you can compare your answer after you complete the derivations. Okay, so the question is, and I think what I can do is, I can maybe show the schematic diagram as well before you do that. That would be better. The previous problem I forgot the schematic diagram, so I'm really sorry for that. And this is the case, right? So here we will have, this is the schematic diagram. Okay, hand drawn one, sorry, but okay. So the question is, water comes out of a tank through a nozzle as an open jet. Okay, the level of water in the tank continuously falls. A streamline in the tank spans from a point 1 to 2, as shown in the diagram, of a curvilinear length approximately kh, where k is 1.5. The ratio of cross-sectional area from the tank to the nozzle is 2:1. Like area of the jet, ratio of area of the opening of the tank to the nozzle is 2 is to 1. Of course, it's very disproportionate from the diagram, but this is what it is shown here. The question, at an instant h is equal to 5 meter, v2 velocity at the exit is 1 meter per second. The local component of acceleration of the flow at the point 2 at that instant of time will be question mark. So we need to find the acceleration component at the instant of time when h is equal to 5 meter. This h is equal to 5 meter. Okay. So yeah. So the thing is now, again, there are maybe various ways to solve the problem. So, but since we are discussing Bernoulli's principle, we will stick to it when we try to find the value of acceleration at that point using the Bernoulli's equation. Okay. So now you can see that since there is a unsteady, element to the problem, that the height of the tank or the height of the liquid at the tank is varying with time, so there is an inherent unsteady element to the problem. Okay. And but we again try to shift towards the Bernoulli's equation because of the fact that they are saying something about the streamline. Okay. So now you can see that where we are actually going. So there is an unsteady element, but there is an element of this Bernoulli's equation as well, because we are dealing with a streamline, flow across along a streamline. Okay. So we'll stick to that intuition and we'll apply the Bernoulli's equation along a streamline, but for unsteady flow. Okay. Of course, keeping in mind the other assumptions that are required for the validity of the Bernoulli's equation are satisfied. So anyone who is watching the video and trying to solve it, maybe can pause the video for now, and then maybe compare your solution with the result that I will show after the solution. Okay. So this is a diagram, and these are the value of the parameters that are already given. K is equal to 1.5, and we'll see where K will be useful. A1 ratio of A1 to A2 is 2, h is 5 meter, and v2 is 1 meter per second, where v2 is the velocity of the jet at the exit. Okay. So what usually happens is that in this kind of problems we usually take v1 to be equal to 0. Okay. But since, and in the case being that the area of the free surface of the tank usually is much larger than the orifice, that is the open jet, this area, that orifice, like the area of this region, the open surface of the tank is much larger than the orifice through which the jet is coming out. That's why we take this v1 to be usually almost equal to 0. Okay. Which is actually not the case, but as an ideal as a good approximation, we can take v1 to be equal to 0. Okay. But since they already told that the orifice area and the free surface area are in the ratio of 2 is to 1, then we cannot actually ignore the velocity at point 1. Okay. So the velocity at point 1 will be significantly high now. Okay. Of course lesser than velocity at point 2, but it will be significantly high. So considering the unsteady form of the Bernoulli's equation, which is given by equation number 1 here, from continuity equation at point 1 and 2, we will get A1 V1 is equal to A2 V2. Okay. Now this equation would be valid if density is constant. If I just trying to recollect, yeah, this will be constant if the density is this equation will be valid if density is constant. Okay. So from here you can represent, since you know v2, you can, in the equations you can replace v1 in terms of v2 because the area ratio is given. Okay. Now since both the points, point 1 and point 2, are open to the atmosphere, then pressure at point 1 would be equal to pressure at point 2. Okay. Then again at a particular instant, because we need to find the value of acceleration at an instant where the height of the liquid at the tank is equal to 5 meters, so h is also constant at that particular instant. So z1 minus z2 is equal to h, which is equal to 5 meter. Okay. So the tricky term that we do not know, because pressure terms are resolved, we will find a relation from continued equation. This term is also resolved. That is Z1 and Z2 is 5. So only tricky part is this equation. Okay, so let us get back to the question. Let us see how we can simplify it. So they say that a streamline in the strength, a streamline in the tank spans from point 1 to point 2 with a curvature length of approximately kh, where k is equal to 1.5. Okay, in that case, it is we have to we take a very uh, important approximation. Okay, let us see what. Okay, for this kind of problems, and I think this was also discussed in the class also. So uh, let me go back to the solution. So we need to simplify this term now. Okay, so we have integration of 1 to 2 dou v by dou t ds. So what we do is we consider that the variation of velocity along the streamline is almost negligible. Okay, that's a very that that's what we approximate, that at a particular instant of time the velocity v1 must remain constant along the streamline. Okay, velocity remains almost, we assume that the velocity remains almost uniform along a streamline. Okay, so that's what our fundamental assumption that we make to simplify this equation. Okay, so if that's the case and the integration is from with respect to the spatial coordinates, that is the spatial streamline coordinates, that is ds. So what we can do is, if that's the case, if we assume that the velocity along the streamline remains almost constant, then this and that's why we have taken the subscript s1, because whatever is the velocity along the streamline at point 1, we assume that if it's the same streamline, the velocity would be constant along the streamline which is the velocity at point 1. Okay, so we can take this integration out of we can take this term out of the integration and convert this partial derivative to a complete derivative, because ideally velocity is a function of both space and time, if you know, because of the Eulerian approach. But we are saying that we can make a simplified approximation where we can say that this velocity is along a streamline remains almost constant, so there is no dependency of velocity along a streamline along the spatial coordinates. So then this velocity becomes only a function of time, so this partial derivative now becomes a complete derivative. And since moreover since this integration is done along the length of the streamline along the spatial direction, so we can take this derivative out of the integration and then simplify it as dv1 by dt times integration of ds from 1 to 2, and ds, as they mentioned, is equal to k times h, as it already mentioned in the question. So our simplified form of this expression turns out to be ks times dv1 by dt. Okay, now so the final form of the equation, Euler's equation, that is equation 1 in this case, can be represented as v1 square minus v2 square by 2 plus gs is equal to kh dv1 by dt. So this dv1 by dt is indeed the local acceleration that we need to find. Okay, so I'm sorry, it has to be v2. Right, so we know v2, so we can represent v1 in terms of v2. Okay, so let me just check. I think I made a mistake here in the expressions, so let me just correct it. Okay, yeah, I think I made a mistake here, so what I will do is I'll correct it. Okay, sorry for that. So let me go back here. Yes, that's fine, yeah, that's fine. So v2 we know, so we have V1 A1 is equal to V2 A2. Okay, so V1 would be V2 times A2 by A1, correct? So we can take V2 common here, so V2 square we can take common, so we have A2 by A1 whole square minus 1, okay, plus GH is equal to 1.5 times H times dV1 by dt. So we need to find dV1 by dt. Now if you substitute the value of A2 by A1, that is equal to 2 in this case, V2 of course, and A2 by A1 is equal to 1 by 2, correct? Let me just verify it. Area of the tank, the nozzle is 2:1, so A2 by A1 is 1 by 2, correct? So, and V2 is 1 meter per second, and G is 9.81, H is 5. So if you substitute the value of these parameters in this equation, you will get dV1 by dt is approximately equal to 6.49 meter per second. Okay, okay, it may not be the exact value, but it will more or less be same. Okay, so that's how you will do it. Okay, I think the only confusion that might arise is this one, considering velocity constant along a streamline. Okay, so it's something that I referred from the lectures. Okay, and something that you can usually do to simplify this kind of expressions. Maybe if required, I feel I may repeat this, not the solution but the concept. Maybe I will discuss it again in the next week's class, and also the question related to the streamline coordinates. Okay, so we'll discuss all of both of them. Okay, meanwhile you can maybe try to take similar problems and try to understand the boundaries equation, the application boundaries equation, and try to solve similar problems. Okay, so I think that would be all from my end today, and thank you for attending today's session, and have a nice evening.